So it's about 7 o'clock, so why don't we get started, and some more people might trickle in. So we are very excited to have Professor Nassar here with us to talk about linear induction motors and maglev. You might recognize him if you were at the in-person CHC event this past May, because he was one of our jury members. So he's going to do a little presentation for us, and then feel free to ask him any questions you might have after the presentation. So I will let you take it away, Professor Nassar.
Okay, I don't know if I can share my screen.
Oh, Justin, should he be able to share his screen, or do you have to give him permission?
I think I will need permission.
Oh.
You should be able to share.
So there's a little.
No, yes, yeah, I can.
Oh, you can? Oh,
yeah.
perfect.
So you can see my screen?
Yes, I can see it. Mm-hmm.
Okay. So welcome everybody. So it is kind of short presentation, but the questions that will come from it will be most of our meeting today. So you are familiar with Hyperloop or the pod design. What are the different components of the Hyperloop? My expertise is with the linear induction machine, some sort of battery system, DC to DC converters, power electronics. I have no clue about the shell or the mechanical system, the suspension. So today we will just focus on the motor part of the pod. So motors, they are around for many years, and there is a lot of advances happen to motors, and rotary machines are well modeled, and they are well designed. If you ask any electrical engineer to sketch a circuit model for linear induction machine, not linear, for induction machine, he will sketch it. It's similar to transformer, same equivalent circuit. The only difference that the resistance of the rotor is function of the slip between stator and rotor, or function of your speed. Once you get to induction machine, and induction machine is just you are cutting the machine and you are rolling it flat, the model will not be working fine. Okay, even theoretically it should be the same. Just when you look at the electrical model of machines, you look at coils, and between them there's some mutual inductances, and that's it. So what will make the linear induction machine different? Why the model is not accurate? So typically the model is not accurate because what we call the end effect. So if we say that, let's take the first picture here. If we say that the linear induction machine is our main stator part, and the back sheet or the secondary sheet. So the main part here will be sourcing or creating flux. So you will have flux going through the primary core and the secondary core, which is similar to what you have here. You are creating flux, and the flux is linking the rotor and the stator through some sort of air gap. And if you look here, we still have the air gap. We have a flux linking the stator and the rotor, but the issue is here. The issue at this part and at this part. And these two parts are not the same for rotary machine. For rotary machine, there is no start and end for the motor. Okay, it's a continuous magnetic circuit. So the flux will go up and it will continue and come back. So if you sketch the flux, it will be going in a semicircle on this side and semicircle on this side. But here you have what is called an end effect. There is open parts here. Also, here you can, because you are rotating the machine, you can have very thin air gap. You can reduce the air gap size. And the air gap reluctance is so high compared to the core reluctance. Usually core reluctance is 5,000 times, sorry, core conductance, permeability, core permeability is 5,000 times air, which means that the resistance of air is at least 5,000 times the resistance of the magnetic core for magnetic flux. In this case, you try to minimize the air gap so you get more flux. For rotary machine, you can minimize the air gap. You need just some sort of space so the rotor can rotate. But for linear induction machine, you will have a large air gap between your stator and your sheet. And this is because of the mechanical design. You will try to minimize the air gap, but it will be in the range of millimeters. And this will make your circuit challenging. Still, the larger air gap means you are taking more current to magnetize the core. But this is a big issue when you are doing control. The stator part, you will have to design it. We can talk about the design of the core and why it should be three-phase. But these are the basic differences between linear induction machine and rotary machine. Bigger air gap and end effect. Let's talk about the end effect, which is the most interesting part. So the end effect, when your primary is moving, it will be moving through the secondary. So at each instant, the primary is leaving one already magnetized part of the air gap, and it is magnetizing a new part from the secondary sheet. So you are leaving an already magnetized piece of iron, and you are magnetizing a new part of iron. So you are adding new part to the magnetization, and you are leaving part from magnetization. So this is added new part will increase your magnetization current. But if you go to the rotary machine, as you are rotating, already this part is magnetized and it is moving from under one magnet to under another magnet. Okay, so you don't have to magnetize new part in your machine. And when you are magnetizing a new part in your machine, you take what is called magnetization current or inrush current. So this machine will be in continuous transient. So at each instant, a new piece of fresh metal is getting under the flux or the primary, and you are leaving behind an already magnetized piece. This end effect is considered as losses. Okay, so because the part of the machine that you are leaving behind, whatever magnetic field inside it will be lost in eddy current. Okay, and the one that you are magnetizing again, it will react. There will be a reaction from the iron against the magnetization, which will create also eddy current. And these eddy currents are useless. They are not producing any thrust. So this is our losses. One of the models, and when we say one of the models, because there are many models for linear induction machine, but this one is the most used one. And this is the one that I used during my master degree. This one is adding a factor to the equivalent circuit, and this factor is this function here. Do you see my screen? Or sorry, you can still see my screen. Yeah, because I disconnected at my side. So if you look at this circuit is a well-known circuit for induction machines, where you have the stator coils, resistance and inductance. Then you have the rotor coil, resistance and inductance, and the rotor resistance is function of the slip. And the rotor resistance here is function of the slip, and the slip is function of the speed. Okay, so the slip is the stator ns minus nr over ns. So this is the synchronous speed minus the rotor speed divided by the synchronous speed. So the slip is function of the speed. So this is the model for induction machine. You have R and L for the core. This is the core equivalent. You have the rotor equivalent. You have the stator equivalent. The rotor equivalent, the resistance is function of speed, and it changed with the mechanical load. So the mechanical load actually is modeled by this resistance. So this resistance actually is modeling your mechanical load. Now, when we use this model or this circuit to model the linear induction machine, the simulation results are not matching the experimental results. So they start to add this factor here, fq, this function here. And this function fq is 1 minus exponential minus q divided by q. And this is how q is calculated, okay? So q, this q factor, is function of your speed. So the core branch, this is the magnetic core branch. The core branch now is function of speed. We can understand that the rotor resistance is function of speed because this is the electromechanical energy conversion. So the energy will cross from the stator to the rotor. The energy that will arrive at the rotor will be divided. Some energy will be lost in losses inside the resistance. The rest of the energy will be converted to mechanical energy. And the ratio that is converted to mechanical is 1 minus S over S ratio of the energy that you are losing. When you add them together, you will get this resistance over S. So R rotor over S is two parts. One is resistance and one is virtual resistance to mimic or model the mechanical energy, which is fine. But now here's the core itself. The magnetization branch here is function also of speed. And here you can see that Q is inversely proportional to speed. So if the speed is 0, U will be infinity, which will make your function here 0, which will make the losses here in this core disappear, and the core will become back as only L magnetizing, the magnetizing reactance of the core, which is the typical induction machine model. So the typical induction machine model, this function of Q will be 0, and this will be it if the machine is stationary, okay? It's not moving, so there is no end effect. As you start to move, as the things getting worse and worse, as you have more end effect, and the end effect here means this value here is getting larger, so you have more losses in the magnetization branch, and you have less magnetization, okay? And you know, instead of working in the ABC model, we call this the ABC model, the three-phase model. So this would be the per phase equivalent circuit. So V here is the per phase voltage, or the voltage of single phase. And we cannot deal with three-phase circuit models. If you do control, this will be a big issue, the ABC model. So instead of using the ABC model, what we usually do, we use what is called the DQ model. So we move from ABC model to DQ models using Park's transformation. So we can go to the DQ model. So this is the D circuit, and here's the Q circuit. And the DQ model is similar to the ABC model, just you have some dynamic EMF generated in the models. And the good point about the DQ model, that you can use control easily. You can do a control in the DQ model easily. I have this paper which is related to what I was doing in my. Okay, let me open this. This is not my research paper, but this is talking about what we are covering here. Here they called the K, or the function of Q, they called it as K. So they multiplied the inductance with a factor K, and this K is the function that it changed with speed, and they modeled it here. Now, if you look at, this is a most important part here. If you look at this speed time curve, okay, and here he is comparing between the given speed and the actual speed, you will see that they are focusing more on the low speed range. And this is the issue with the model. So this model that I was just presenting here, this model here has issue with low speed. It is not representing the machine perfectly at low speed. That's why there is a lot of research how you are going to model your machine. One of them is this model here, and any researchers that he will say, okay, my model is working fine, it's working better, just he will focus on the low speed. Okay, let me bring the controls he have. Okay, so here is the inverter that is controlling the LIM, the linear induction machine. So this inverter output will be in the ABC model, in the three-phase model ABC. Then you transform it to DQ in the DQ model, so you can do your current control. So you have ID and IQ references, you compare them with the current, and you get the voltage VD and VQ, you feed it for the inverter, then you get your VABC. So how accurate is your LEM model is very important in estimating the parameters of the control. Also, you can see here, this is one type of control. This is the speed and thrust, or the torque speed characteristic. So the torque speed characteristic of linear induction machine is the same as any induction machine. Okay, this is the same shape you will see for induction machine. This is, you can remove this and say this is torque, here is a speed, and this is a torque speed curve. But they are sketching this at different frequencies. So if you do frequency control, which is similar to field control in DC machines, you can see that the maximum torque is going down, but you are getting higher speed. Okay, and this is what you should be doing in your pod control. So in your pod control, you should do frequency control, because you need high torque at starting or high thrust to get your pod moving. Then you need speed. You need to convert this to speed. So you will be doing something like this. You will be doing a frequency control. But when you are doing frequency control, you can see that your maximum thrust will be falling down with your speed. For traction control or for driving traction, that's fine, because mechanical load will getting less as you move. But the problem will be with the dragging force. Given that this pod will be in a vacuum tube, we are not expecting a dragging force that is proportional to speed square. So this would be fine. But this paper is very good in modeling. Their model is more accurate. They removed the resistance with Q factor, and they added this factor here with R rotor. So they changed a bit the model from the model that we had in our presentation. And you can tell is it a good model or not by looking at how it perform at low speed. If it perform well at low speed, he's capturing the dynamics of the limb. So okay, sorry, I changed this. So actually, this was my master's thesis, is modeling and control of linear induction machine, and I had issues with the low speed. I had an error at low speed. So if you go here in the paper just to see. You will see that they are trying to follow where they have it. Yes, here. You will try to follow a speed profile. So you will start by acceleration, then you will go with constant speed, then you will start to decelerate until you stop. So this is the typical speed profile you will have. You start by accelerating, running constant speed, then decelerating until you come to complete stop. The problem you will have will be at the low speed during the first acceleration and at the low speed during the last deceleration. But I can see from this model that they were able to have negligible error at low speed. Okay, you can see the difference here between 7.85 to 7.5. This is 0.5 out of 8. So the error here is so negligible. And if you want, we can go through the design or the winding layout or the control itself. I don't know what you need to hear more about. Just I had a general slides about the linear induction machine, its model. But I'm okay with any part you need to elaborate more. So I will stop here my presentation and take your questions, and I will connect my iPad so we can discuss your questions.
Thanks so much, Professor Nassar. That was great. So if anybody has any questions, you can either type it in the chat or you could turn on your camera and ask Professor Nassar the question yourself. So yeah, go for it.
Okay. Hello, can you hear me?
Yes.
Okay. Could you just go through the winding configuration if you have that?
Yes. Let me. I'm connecting just to my iPad, so it's better to do the winding configuration.
Sure.
See how. I'm trying to connect. Can someone send me a link to join the meeting so I can join from the iPad? It is not showing in my iPad calendar.
Yes, I can send that to you. 1 second.
Thank you.
All right, I just sent it.
Okay, let me open it from here.
Give it a minute or two to come through. Or here, better yet, can I put it in the chat of this call?
For some reason, it is not showing. You know, sometimes there is two Teams accounts attached to your email. One is a personal one, and one is a work one. For some reason, the one I see here is a personal one. It's same email, but it's not showing all the notifications. So if you send me an email with the link, just I will open it from the email.
Okay, I just sent it, so hopefully it goes through. I also did put it in the chat, if that's helpful at all.
Yeah, it didn't appear at my side.
All right, I think it just sent.
Okay. Yes, I received it. Yes, I'm joining now. Let me know when you see my screen.
Yes, we can see it.
Oh, okay, so you can see my iPad screen.
Yep.
Okay. So for winding, the basic idea whenever you are doing winding is how many poles you need to design, okay, and how many phases. for phases, we will stick with 3 phase, okay? Because we need a rotating magnetic field. This will be a linear induction machine, so we will stick to 3 phase. Now, how many poles? So whoever asks the question, how many poles you need to design?
We can just go with 4 for now, I think.
Okay,
4
so
poles.
let's say 4 poles. Okay, so 4 poles means you will have a north, south, north, south, correct? And so you will have north, south, north, south. Okay, so you will do this as 2. Okay, then you have another 2. Whatever you will do for the first 2, you will do for the second 2. Now, under each pole, you will have 3 phase. Okay, so you need to add ABC here. You need to add ABC here. Okay, so let's take one pole and look at it. Okay, or one pair of poles. Okay, so this would be north, and this would be south. Okay, so the idea is we need to generate rotating magnetic field out of our magnetic flux, and we need a sinusoidal wave for our magnetic flux. So we will do the following. So how many degrees is this electrically? So what is the electrical angle for one pair of poles?
Is it 120?
No. So okay. So let's say you have a north pole and south pole. Okay, and they are rotating. If you look at the sine wave they are generating, you will generate north, then you are generating south, which means this is 360 degree. Okay, if you have 4 poles machine, so you have north, south, and you are rotating, so you are generating north, south, so you are generating 720 degrees. We call this angle the electrical angle. We call this angle the electrical angle, and your angle of rotation here is called the mechanical angle, theta mechanical. You can see here mechanically, when you rotate here, mechanically you will do 360 degree. Electrically, you are doing 360 degree. But in this case here, when you rotate, you are doing 360 degree, but actually you are doing 720 degree electrically. So the general rule that theta electrical is P theta mechanical. Okay, so the electrical angle is the number of poles, pair of poles. This is pair of poles multiplied by the mechanical angle. Okay, so if we have one pair, theta electrical is the same as theta mechanical. You will rotate 360 mechanical, you will get 360 electrical. If we have 2 pair of poles, theta electrical will be double theta mechanical. Okay, so the rule is each one pole is 180 degree electrical. This is a rule, it will never change. So under north, you have 180 degree. Under south, you have 180 degree. But this angle is electrical angle, not mechanical angle. Okay, because the mechanical angle will depend how many poles you have inside your machine. So if the whole machine has 2 poles, north and south, so each pole mechanically will cover 180 degree mechanical. But if I divided my machine into 4 poles, north, south, mechanically each pole will cover 90 degree mechanical. But still electrically, it is a sine wave. It will cover a positive half of a sine wave, which means electrically it's 180 degree. So the electrical angle is constant for the pole, but the mechanical angle is not. Okay, so when we look at here, we took this machine, okay, and we divided it into 4 poles, okay. So, and the machine is number of slots. So let's say that our machine here is 36 slots. So how many slots we will have under each pole?
9.
9. So we will have 9 slots under each pole. So if we sketch 1, 2, 3,
Is there any particular reason why you chose 36 slots?
No, just it has to be
Okay.
divisible by 3.
Okay.
And the number of poles you have, which is 4. Okay, so this is the number of phases. This is the number of poles. It should be divisible by this number. So it can be 12 slots, it can be 24 slots, it can be 36 slots, 48. Okay, so this is the rule. It has to be divisible by number of phases multiplied by the number of poles you have. Now, if you look at, let's say this is the North Pole, okay? So this is the North Pole. Then we will have same under the South Pole. Okay. And this will be under South Pole. Okay. And now you have 18 slots in total, and this is this part. This is 18 slots, and here we have 18 slots. Okay. Now, don't forget that you have a 3-phase supply. Okay. So if we look at our supply versus omega t. So let's say this is VA, and VB will be here. VB, and VC will be somewhere here. Okay, so this is VC. So this would be your 3-phase voltage or current. Okay, so at any instant, if you take the 3 values here, you will see that the summation of the 3 will be 0. For example, here VA is V maximum, while VB equal VC equal negative V maximum over 2. So if you add them together, it will be 0. But you can see that at least one of them will be, or group of them will be positive, group of them will be negative. So the current is going and returning in the other phase. Okay, because you have A, B, and C, A, B, C. So in our case here at this instant here, you can see that A is positive, B and C are negative. Okay, so they are returning. So the current is going from the source into the coils, then it is returning back to the source. Okay, so the current will flow from the source into the coils, then it will return in the other parts. So the summation of the current at any instant is 0. Okay, if you take this instant here, you will see that B and A are positive V maximum over 2, while VC is negative V maximum over 2. So the current is coming from A and B, I over 2, I over 2, then it is returning as I here. Okay, why we are talking about this? Because this will be the direction of flux. Okay, so when we are creating phase A and phase B and phase C, the current will be entering in one or two of the phases and returning in the other. And we need to make sure that this current is creating a flux that is shifting with time. Okay, and to do this, we have to space our coils with the same electrical space. Okay, so you can see here between phases. So this is phase. Sorry. Here phase A start here, phase B start here, phase C start here. So between phases, we have 120 degree. We have 120 degree between phases. So this shift is in time. This is the excitation to the coils. So we need to excite coils 120 degree shift in time, which will be done by the supply. The supply will be 3-phase source coming from your inverter. But we have to space the coils mechanically or physically 120 degree. Okay, and this 120 degree is measured it is mechanical space, but it's measured electrically. What does this mean? I need between my coils, when I lay them down in the slots, to have 120-degree. Now, what is the angle under the north pole? What is the total angle?
180.
180, which means that each slot here is actually 20-degree. Okay, so if I start to my A coil here, if I start my coil here as A, I need to start B after 120-degree, which means I need to have 6 slots. Okay, so I will start to count 20, 1, 2, 3, 4, 5, 6, correct? So I should start B here. So B should start here. Okay. Now where we should start?
When you say starts, do you mean that's where you supply that's where the input for the second phase starts?
Yes. So let's say in the circular case, okay, in the circular machine, okay, and let's say that this is our north pole, okay, because we have 4 poles machine, okay. So this is the north pole. So inside the north pole, between here and here, it's 180-degree electrical. Okay, you know this, it's not mechanical, we look electrical. And we have slots here. So if I start to do a winding, okay, I will take 1/3 of this winding. Okay, so a winding will space 1/3. So if I start to do winding A here, it will cover a space. It will take 1/3 of this pole because I'm dividing ABC. So each one will span 1/3 of the pole. So this is the start of A. Here where I will start doing A. Now, when you do coil, let's say we are creating a coil. So we start by this side 1 of the coil. And this side has to be under north. So the current is entering here. Then this current has to leave. Okay. So the current has to leave under a north. So you are creating a flux going up here. And you are creating a flux going the other way here. Okay. So according to the right-hand rule, so the flux will be going up here. And the flux will be going down here. Okay. So this is the start of phase A. So the first side of the coil will be under north. The second side of the coil will be under south. Okay. We don't have to do this. This is one way of doing winding. We will see the 2 different ways to do it. Okay. The lattice one or the second one. Any benefits from more than 3 phases, Taha? There is what is called multi-phase machines, Taha, which will give you a smooth torque. It will act like DC, more like DC. So there is still some research for, I have a colleague doing research in 9-phase machines. It's called multi-phase machines. This will give you smoother torque. Look at the 3-phase machine as you have 3 pistons, motor with 3 pistons. What if I have 6 pistons? What if I have 9 pistons? So this can give you more force and more steady force. Okay, now, so if I start here A, okay, so I will start to lay down A, then I will return after 180-degree. So I will return here. Okay, now how many slots that A should span? So I have 9 slots divided between A, B, C. So A should span 3 slots. So I will continue doing this. I will continue A here. And then I will continue up to here. So this would be the end of A, and this would be the start of A. Another way to do it is to go in the outer and then go in the inner one. The difference is how neat your end coils. So you don't want a messy coil on this side. You need this coil to be smooth and well structured, not to disrupt your magnetic flux. So instead of doing it like this, instead of going in this lattice structure, we can do it like this. We can start from the end to the end and then going like this. Okay, so you start at 1, instead of returning at 9, you return at sorry, instead of returning at 10, you return at 12. So you go 1 to 12, okay, then you go to 2 to 11, then you go to 3 to 10. Or you can do it 1 to 10, 1, 10, then 2, 11, then 3, 12. Or you can do it 1, 12, then 2, 11, then 3, 10.
Okay.
Either way is fine.
And they'll behave the same way for all types of configurations.
Okay, so the idea is how you create flux. Okay, so if you feed current here, I will go here, it will return here, it will go here, it will return here, it will go here, it will return here. So all of this in same direction, creating flux in same direction. All of this in this direction, creating flux in same direction. This is a rule, is how you create flux.
Yeah. Okay.
We don't care about how you connect them. So this is for electrical continuity. Okay, you need electrical continuity. So this is for electrical continuity. So what you care about is how the flux or current is going inside the slots. This is how the flux will be generated. Could you expand on exactly what is a phase? What is a phase? Okay, if we look at anyone here from Sam, are you from mechanical background? If we explain mechanical, you will get the idea. You are from electrical background? Okay, but new. Okay, that's fine. Okay, so let's explain this in mechanical terms. Okay, so if you have a piston, okay, if you have a piston and you are using a single piston machine, so this piston, once you have a spark here, you will get a force. Once the piston is going down in another stroke, you are not generating any force. So the force you are getting from the piston will be increasing. Then this piston need power to go up. So the power you are getting is not constant, it's changing. Which means if I'm driving my car with this piston, I'm not getting a smooth constant power. The power will be going up and down. To solve this, they said, okay, let's add a crankshaft and let's add 3 pistons and it changes their positions. Okay, so in this case, I can synchronize them. So at any time, I'm getting a constant power from all of them. Okay, which means that the first one will generate a wave. The second one will generate a wave shifted. The third one will generate a wave shifted. If you take the total of these, you will see a constant power output. They will call each one of these as phase. Phase 1, phase 2, or phase 3, or source 1, source 2, source 3. So in circuits, we use 3 sources connected together, not one source. Each source has its own voltage. The first one starts from 0. Second one start shifted delayed by 180 degree. Third one start leading by 120 degree. And you can adjust this by adjusting the coils inside the machine. And we call them phases. Phase A, phase B, phase C. Or source A, source B, source C. Okay, each source is a sinusoidal supply. It's an AC source, but they are shifted in time domain. Make kind of sense? Make sense? Okay, now, so following on this, once we finish the A, we need to do B winding, okay? So B winding, it has to be shifted 120 degree from A winding to be spaced So if this is coil, if this is a machine, okay, if we add coil A here, we need to add coil B 120 degree. We need to add coil C 120 degree. So from A, I need to start B after 120 degree. So I will start B here. Okay, so B will start here. Then between the going and return, I need to go under north and return under south. So I need 180 degree. And 180 degree in terms of slots is 9 slots. So from here, I need to go 180 degree. 180 degree means I need to go 9 slots. So here is 1, 2, 3, 4, 5, 6, 7, 8, 9. So I should go up to this slot here. Then I need to cover 3 slots under this pole for phase B. So this would be the end of B, and this would be the start of B. For phase C, I need to start 120 degree from B. So after B, I will count 120 degree. Okay, and 120 degree is 6 slots. So 1, 2, 3, 4, 5, 6. So I will start C here. This is where I should start C. Okay, so I will do C. So I will start doing C here. So this would be the start of C. Now what we need to do, we need to return after 180 degree, which is 9 slots. So 1, 2, 3, 4, 5, 6, 7, 8. So I will return here. Then I will go back to the next slot. Then I will go back to the next slot. Then I will go back to the next slot. And I will go back to the next slot. So this will be the end of C, and this is the start of C. Whatever I did here for the first 2 poles, north and south, I will do the same for the second 2 poles, the other source and south. Which means at the end, this is what I will have. I will have the following. I will have a start of A and a coil called A between, then end of A. A start of B and the coil called B and the end of B. A start of C and the coil called C and end of C. Okay? And I will have the same, so don't forget that the current is entering here, leaving here, okay? For each phase. I will have the same under the second pole. Okay, I will have the same under the second pole. So this is under the first pole, north and south. So I'm designing my machine to be north-south, north-south. So I need the current to enter under the north and return under south. Then I need this current to enter to create another north here and return. So I will connect a start of A1, sorry, end of A1 with the start of A2. And end of B1 with the start of B2. And the end of C1 with the start of C2. It's like I'm connecting them series. By the way, if you changed this connection, you connected end of A1 with end of A2. In this case, you are creating here north and here south. If you look at the arrangement, it will be north, south, south, north. Now, how many poles you have here created? 2 poles instead of 4. Okay? By just changing the interconnection between the winding. And this is, you know, this fan, ceiling fan, which has this down chain that you can change the speed. It has a switch that changes the connection from 2 pole to 4 pole, which you can change the speed.
Yes.
So this is the cheapest speed change you have as terms in control, but you are winding the machine to work in 2 pole or 4 pole configuration. Okay, and you can do this by switching. Okay, and when you change the number of poles, you are doubling the speed. That's why the steps are higher. Okay, you are going from a speed to double the speed to double the speed again.
Yes.
That's why the steps are not smooth.
Say so. For like normal rotary induction machines, you can change the pole in like a 2-to-1 ratio quite easily. Is there any reason why this can't be done for linear induction machines? So like you're saying, you can halve the number of poles easily in a rotary induction machine, can this be done for like a linear induction machine to like as a means of like
Same
controlling the
concept.
speed?
Same
Yeah.
concept. Same concept. Same concept. Yes.
See. Okay. If you just go back to your winding diagram.
Okay, this will create some issues with transient when you change this. If you are running, and while you are running, you change the number of poles, you need the rotor to follow this number of poles, because the rotor poles are generated from the stator poles. So this can create some magnetic transient, but that's fine. If your machine can take it, it's okay. So that's why we do this pole changing for a small sized machine, because the transient will create inrush current, and this can create some issues.
Okay.
Oh, the
So for
ceiling
like
fan motor is not that big.
Yeah. So for like a larger machine, that's like, I don't know, like that's you'd be used for like transportation. This is not going to be a good idea to change the poles.
No. It's easier to change frequency. You can make your magnetic flux going faster, and this will change your speed. Okay, but you need an inverter, and the inverter cost is high. It is 1.5 to double the motor cost. For ceiling fan, I will not buy a VFD to control its speed. Okay, it doesn't work to do this. So
Yeah.
let's increase the size of coils so it can withstand the transient, and do this using a mechanical switch, even it's a mechanical switch, to change the poles.
Yeah.
Okay.
Okay.
But
Makes
the
sense.
only difference between a 2-pole machine and 4-pole machine will be how you wire the coils. Okay, so assume that we will follow your design. So we have this as 4-pole machine, so we will wire it like this. Okay, end of A with the start of A2. Okay, so the current will be exiting here, entering here. So you are creating north-south, north-south. Now, at the end, you will have the following. Okay, you will have one start for A, one end for A. Then you have one start of B, one end of B. Then you have one start of C, one end of C. Doesn't matter how many modules you have inside. If you have 6-pole machine, A will have 3 modular winding connected in series. B is so. But at the end you have one start. At the end you have one start and one end for A. One start and one end for B, and so on. Now here you can connect these together in star or delta. Okay, so you can connect this as a star. So you connect these points together. Then you have your 3-phase A, B, C. These are your 3-phase winding. So you will connect this to the star, to the supply. Okay. So this is a neutral point, and here is ABC. Okay. Now, when you connect a star, you are opening the path here, which is the path for the third harmonics. Okay. So you are preventing any third harmonics from flowing into your machine. Your impedance for third harmonic is infinity. No third harmonic current can flow in your machine. Okay, which is good. So this is a good thing to do. But the voltage across the phase, the voltage across one coil is V phase. So the voltage across one coil is V phase. The other option is to connect the machine or the coils in star configuration, in delta configuration. Okay. So in delta configuration, this is how you connect it. Start A, end A, start B, end B, start C, end C. Okay. So you take the start of A, and you connect it with the end of C, and this will be your terminal A. Then you take the end of A and you connect it with the start of B, and this will be terminal B. And then you take the end of B and you connect it with the start of C, and you call this as C. Now, any third harmonic current, okay, any third harmonic current will be flowing inside. Any third harmonic will be flowing inside the machine. So by connecting the machine as delta, you created a path for your third harmonics. And your third harmonics will be flowing only inside the machine. They are trapped inside the machine. They are not going outside. So I third will be going here, I third will be going here, I third will be going here. I third is not sensed at the current outside. No third harmonic outside. The issue with this configuration that this third harmonic current will be heating up your machine. It will overheat your machine. But what you get from here is that the voltage across one coil is the voltage between A and B. So the voltage across one coil is √3 V phase. You see higher voltage, which can give you higher speed, okay, and higher power, okay. But the issue with this, any third harmonic will literally damage your machine. I think we had this issue, Taha, one time. We had third harmonic. You grounded the neutral, something like this. The same here. If you grounded this neutral, you are creating a path for the third harmonic. So never do this. Okay, so you are creating a path for the third harmonic, which will literally burn your coils. Okay. Makes sense how we are creating winding. So how you will connect the individual winding together, and then how you will connect all the winding in star or delta at the end.
Yeah, it makes quite a lot of sense now.
If you are decided to connect your machine as delta, all induction machines, rotary machines, are connected delta because this gives you higher torque for the same voltage. You know that the torque is proportional to V square. So if I increased my V phase, if I increase my V phase by √3, I'm getting 3 times the torque from the same machine. Okay, but the issue is you are overheating your machine with the third harmonic current, which will limit the maximum current. Okay, so it's a trade-off. But you can do what is called shorting the motor span or the coil span to eliminate the third harmonic. So to eliminate the third harmonic, I need to shorten my coil span by 60 degrees. So I need to shorten by pi over the harmonic I need to eliminate. If I need to eliminate the third harmonic, I need to shorten by pi over 3. And what is shorting means, okay? So we said you start here, start A, then you return after 180, okay? And the span of the coil is 180 degree. You shorten this by 60 degree. Okay? In this case, instead of when we are doing the winding, we are going from 1 and returning here, we will return 1, 2, back. Okay, so we will return earlier, and this will reduce the third harmonic. And if you look at the flux, okay, if this is a flux, okay, so we start here, start A, and we return here, okay. So this would be the north, and this is the south. And the flux you are creating inside the machine is actually a square wave. You are not creating sine wave. To create sine wave, you need the slot size to be 0 degree. So you need infinite number of slots. Okay, so to sketch a sine wave, you need to have your flux wave something like this. Okay, so if you have 3 coils for A here, so this is A, so you are going like this. This is A. So what you are doing, you are adding flux to flux to flux to flux, then you are returning. So this is what will be the shape of your flux. This is the north and south. If
So
you have more slots,
the more slots you have, the better it approximates a sine wave.
Yes, and we approximate this in a sine wave. So the larger your slot size, the more square your flux, the more saturation and harmonics you have, which is not recommended. Okay. Now, if you shorten this by 60 degrees, you will have something like this. And if you do Fourier transform for this wave, you will see that the factor, we can prove this if we have time. This is pi over 2. We can prove that for this shape, with this angle as pi over 6, that the third harmonic will disappear. You don't have third harmonics. We can do this by Fourier when you study Fourier. Okay, but this is called chording or shortening the winding. But you will do this if you are going to connect your coils in delta, and if you manage to do this, you will get really high torque, because the voltage that you will apply will be √3 V phase. So your same coils and your same insulation that was withstanding 100 volt, now you can apply 170, because you are connecting in delta instead of star.
And this is called shorting the winding, shorting the third harmonic. What was this called?
It's called the chording. Okay, I can search for that term. They called it pitched coil. Okay, let me share this. This is a well-known technique. You can see this screen. It's called chording. Okay? And the chording is called chording factor. You can see it. Sorry, you can see it. Or...
Yeah, you can.
Okay,
Chording
it's called chording. Okay, so the term is called chording.
and harmonic.
So look, to eliminate the fifth harmonic, you need to chord it by 36 degrees, which is 180 over 5. Correct? And 60 degree, it will eliminate the third harmonic. Okay. So I will go back and share the iPad screen. Okay, so does this answer your question about winding?
Yeah, it does. The only thing was that when you drew the windings with the 3 phases, if you scroll up to the top again, further up. Yeah, here. Okay, this makes sense for a rotary machine. How would this arrangement be configured on a linear machine? Because the C phase, it kind of like goes off to the right and then comes back from the left. How would you do that on a linear machine?
In this case, what you will do, so
would it be hanging off at the end, on the end?
Okay, so this would be your phase A. Okay, then you will have your phase B here. Okay, then you will have your phase C here. Okay, but you will be supplying it from this end. Okay, so you do A, you do your A, then you do your B, Then you do your C like this, okay? And you will supply C from somewhere here.
Okay, so from the right instead of the left.
Yes.
Okay.
And there is many other configurations that we went through. As I remember, Taha, there was some funny modular ways to do it. So at the end, what you need to do, you need the current to be going when you have north, then you need the current to be going out when you have south. Then you need this north to be shifting with time. Okay, and shifting with time means you take time, or let's bring the sine wave. Okay. So when you will say, okay, I have a three-phase rotating magnetic field. The idea, if I have a coil, its a flux is in the center of the coil pointing up. Okay. If we have a rotary machine, so the directions will be A direction here, B direction here, C direction here. Okay, so these are the positive direction for the flux coming from each coil. In the linear machine, if this is phase A, this is how we have the winding A. So the direction for flux A will be here. This is phi coming from A. Okay, the same for B and C and so on. So the idea is I need to take instance in time. Let's say we will take this instant here. We will take this one here. We will take this one here. Okay, so we take 0, 30. Then we can take this one here, 60 and 90. So you take 3-4 times in your sine waves, and you say, okay, at the first point A, IA is 0, IB equal IC, or let's write it down. IB equal to IB is okay. IB equal to negative I max over 2, and IC equal positive I max over 2. Then we take the second instant, IA equal IB equal I max over 2, IC equal negative I max. And the summation of current and at any point of this is 0, because it's a 3-phase. Then you try to figure out what is the total flux. Okay? Let's take a rotary machine. For rotary machine, at the first instant, IB is positive, IC is negative. So if you take the total flux will be pointing here. This is instant A, and this is a resultant flux. Then you take the next instant, IB equal IA equal positive I over 2. So they are positive, so they will be summing to something here. Then IC is negative I max, so IC is negative I max here. So this would be the total. Then you find the angle between the two instants, that there is an angle shift. And you make sure that this angle is following the same angle as here. If you did this, you will have a total resultant flux, and this total resultant flux will be rotating at the same frequency of the supply. We need to see the same here. So we need to see a flux north and south. Then I need to see that my north is shifting and my south is shifting with time at the same speed. And how this will be shifting, you take the same instant, take the same current, what is IA, IB, IC, and make sure that these slots here are having the current going inside them, while the current here is going outside, while the current here is going inside, while the current here, it will be the north again, going outside. If your winding is doing this, the current is shifting with time at the same speed of the supply, your winding is correct. Whatever the winding architecture you have, or the winding way you have. We can have another meeting, maybe having another event where we discuss the control, not only the machine, because most of the teams are using inverters, and your inverter itself is generating harmonics, and you have to take care of these harmonics. You don't want any negative sequence harmonics. You don't want any third harmonics. You can have third harmonics in your inverter, given you have an unearthed star connection. We call it open star or 3-wire star. You are not allowed to have 4-wire star. If you have a 4-wire star, you will have a third harmonic current flowing, which will overheat your machine. So the third harmonic fully going into the neutral. Also, how you are going to do control, okay? Are you going to do torque control, or you are going to do field control, voltage control, frequency control, V over F control? What type of control and how they affect your speeding or acceleration? So we can have another meeting to discuss the control, not the machine itself. But for now, let's take questions about the machine. Any questions?
Emmanuel, do you have a question?
Yes.
Yes.
Yes, I have.
Go ahead.
Yes. Hello. Can you hear us?
Yes,
Yes.
Yes.
So we're currently on the testing phase of our limb, and basically what we have right now is a laminated core that's not isolated. So we were wondering if it was problematic to test the limb, especially temperature-wise, if each lamination isn't isolated between them.
Okay, so you know why we do lamination? What is the idea for lamination?
Yeah, is it for a thermal, for a better thermal profile?
No. Okay, no, not for thermal profile. Okay, so let's say this is a core. Okay, and inside this core, you are doing your coil. Okay. Okay, so this core will be subjected to 2 types of losses that will heat the core. One of them is called eddy loss, and one of them is called hysteresis loss. Okay, here we are not talking about hysteresis. It's not a big deal. The problem is with eddy. Okay, so eddy loss, you have a flux here, correct? So this flux is cutting the core, which means that there is potential or voltage difference generated inside the core. Okay, if this core is made from a conducting material, it means it will circulate current. Okay, so the electrical characteristic of this core is related to the current that will be generated inside the core. We don't need any current to be generated inside the core. Okay, just we need the flux to go through the core. So we need a core with high resistance, high permeability, low magnetic reluctance. So we need the reluctance to be less, and the resistance to be high. So we need the flux to go easy, but we don't need any electrical current. Okay, the eddy current or the hysteresis, the eddy loss is proportional to the frequency square. Okay, so the equation for the eddy loss, it's a function of the frequency square. When it is function of the frequency square, it means even if this loss is very small, it will be magnified by the frequency. So imagine that the frequency is 60, so you are multiplying it by 3600. If you do speed control using frequency control, we are expecting your frequency to go to 200, for example, 200 hertz, which will multiply the eddy loss by 40,000. Okay, so this is crazy. If you have this core not laminated, it will melt. Okay, for sure it will melt. Now the idea is that this eddy hysteresis is proportional to the volume. Okay, and this volume, say, power 2.5. Okay, so what we do now, if we divided this core into sheets, Okay. We laminate this core, okay? So, and we add between the sheets an insulating material. So when you press these sheets together, this insulating material is electrical insulating, not magnetic insulating. Okay, which means it will insulate the electric current, but it will not insulate the magnetic field. So for the magnetic field, it will still see the core as one continuous sheet. It is different material, but it's still conducting for the magnetic. But in terms of electrical, you made the area of your sheet very thin because the sheets are isolated from each other. In this case, it will see these as parallel circuits with very thin area. So the resistance will be very small. Sorry, very large. Sorry, very large. Why the resistance is very large? Because the resistivity is, or the resistance is rho L over the cross-sectional area. Okay, this is the total resistance. So what you did here, you divided the area of your sheet to very, very thin one. So you reduced the area, cross-sectional area, which will increase your total resistance, which will resist the electric current, which will reduce the eddy current. If you didn't isolate the lamination and you connected them together, it will become as one electrical connected sheet. So this lamination has no effect. It will be as you created your core as solid. Okay, and just to imagine how this would be harmful to your machine, I will show you a video that I usually run in class. Yes, here we go. Okay, so I will share my screen from the computer. Okay, so here he's trying to get rid of this stud. Now look, so what he has here, he has a coil, okay, and this coil was just a few winding, so his number of turns is just 2, and he is putting it around the stud or the screw, and this screw is solid, okay, it's solid, it is not laminated, and you can see, and here he has an AC supply with high frequency. I don't know if you will hear the sound, but you will hear the sound of the high frequency supply. Now you can see how fast this is getting heated because it's solid. If this stud or this screw is laminated, you will not have this eddy losses. Okay. Now look, he will just put this on the block itself, on the motor itself or the engine itself. Look, just it's a solid piece here, okay, solid. So you can see how much heat you are generating. So if you are not doing lamination, you are doing induction heating. Okay, so you are heating the core. So you cannot even test this. So don't test without isolating the sheets.
Okay, thank you very much.
You are.
Also, excuse me, can we get the link of the research paper that you presented in your
Yeah.
class?
I will post it here in the chat.
Okay.
I added it to the chat. Okay, any other questions?
Is there any more questions from anybody else?
I don't want to be greedy on time, but can I just ask like one more just general question? You don't
Oh,
have to
yeah,
go.
no.
Go ahead.
Go ahead.
So you know with the pole changing, you're saying how if you go from, for example, from 8-pole to 4-pole straight away, that's not going to be feasible for larger machines. But is there a method to like make the transition a bit more smooth, if that makes sense? Like with mechanical gears, like if that concept
No.
can be replicated.
So it is not about the mechanical, okay? So what you have, okay? So the issue is here, okay? You have a stator, okay? And you have a rotor, okay? And in the stator, if you are creating north-south, you are creating south-north here, okay? So the rotor will follow the stator. Now, if you change the stator to be north-south, north-south, this has to flip here, okay? Which means you are changing the magnetization. You are taking, if you look at the BH curve, you are taking a positive flux and you are going with a negative flux. So you will go through hysteresis, some hysteresis losses, and this will be some transient in your circuit. So what will happen is that your magnetic part, which is the inductance of the circuit, will change. It will take more inductive current to do this transition. So what I'm saying is that the current at your stator will increase. You have a transient. If your coils can withstand this current transient, because the inrush current can reach around 5 to 7 times the rated current. So if your motor takes 70 amperes during this transition, it can take like 300 amperes or 250 amperes. This is a problem with induction machines. The starting current is very, very high due to the inrush, due to the magnetization circuit. So can your coils withstand this transition? This is a question. Not the mechanical. It's about the electrical part.
Okay. Yeah. Okay. Yeah. Okay. That makes sense. Thank you.
Okay, and the rule is the synchronous speed is 120 frequency over number of poles. This is the equation, okay? The frequency is 60 if we are running from a constant fixed sublime. So the number of poles will determine what is your maximum speed is. Okay, the other way to do it is let's change the frequency. Let's have a VFD and change the frequency and keep the number of poles constant. But this is more cost because you need VFD. You need a variable frequency drive.
Yeah.
Okay, so for cheap operation, we can change the number of poles, it's cheaper, but the frequency will do the same job.
Yeah.
Even in a better resolution or a better smooth change.
Yeah.
Because you can do the frequency 60, 61, 60.5, but number of poles is either 2, 4, 8, and so on.
Okay. And is frequency control how they usually do it in I don't know, with industrial linear machines to control speed?
So usually this is the inverter part. Okay, so the inverter part, you will have a 3-phase inverter. Say you are using an okay. So you will have your 3-phase supply, A, B, and C. Then you can have uncontrolled rectifier, okay, A, B, C, which will give you a DC. You have a DC link capacitor. Then you have your A, B, and C.
switch 135.462. These are the switches, and each switch here has its own freewheeling diode. This can be an IGBTs, and then you have your output A, B, C. So what you have here, you have a 3-phase with a fixed frequency 60. You are converting it into DC, so no frequency. Then you are cutting it back using a 3-phase inverter to whatever the frequency you have. Okay, but you will get something like this. So you can control how long you are connecting each switch, so you can control this time T. And by controlling this time T, you can control the frequency. Okay, and usually we will have a filter to filter this a little bit, so you can have some sort of a sine wave. So by controlling the time on off of this bridge, you can get a different frequency at the output. We call this PWM, and you can change the pulse width modulation to change the magnitude of the voltage and the frequency.
Okay.
But this will be done at the inverter side.
Yeah.
We can have another meeting to go through how we can do this and the different topologies, because we can do this as thyristor based. We can control the voltage from here and control the frequency from here, or we can do this as a diode bridge front end, and then at here we do the voltage and the frequency changing. And to do this, we can do, there's many ways of doing this. We can do sinusoidal pulse width modulation. We can do space vector pulse width modulation. Each technique has its pros and cons and how it is done. But all of these are at the inverter side.
Yeah. Okay. Okay. Thank you.
Any other questions from anybody? All right. Well, that was awesome. Thanks for answering everybody's questions. That was super detailed and in depth. That's just what everybody needs to keep building their motors. So that's super helpful. And we'd love to have you back for part 2. Maybe I can organize that with you for sometime in November, possibly. Because I think this is just super helpful to all the teams, because there's not too much information about linear induction motors out there, as I'm sure you know. So this is awesome. Well, for everybody who came, I really appreciate everybody coming. This was awesome. Thank you for all your questions. And I will let you know when we are having Professor Nassar back, so you can come back with more. If you haven't already heard, CHC is doing our virtual showcase again. It's happening November 19th to 20th. And if you would like to be a part of it and have your team present, you can find all the information on our website. So just head to cahyperloop.ca and you can find all the information under Virtual Showcase 2022. This year we are allowing teams to present in 14 different categories, and each team is allowed to apply up to 4. All of these applications are due on November 1st, and the link to the form that you will fill out is on our website. So head over there for more information. We are really excited to see everybody's applications and hear your presentations. Make sure to email us at chc@cahyperloop if you have any questions, or you can just DM us on Instagram if that works too. But thank you so much, everybody, for coming. Have a great rest of your night. And thank you so much again, Professor Nassar, for taking time out of your busy schedule to come and talk to us.
Okay, thank you all, and I hope this was helpful for you. And looking forward to meet you again.
Yes, awesome. Thank you so much, everybody.
Thank you.
Thank you.
Thank you.
You.
Thank you.
Thank
You.
Have a good night, everyone.
You too.